Okay, thank you so much. Okay, so welcome everyone. Oops. Thanks for giving me the opportunity to talk to you today. So I will be speaking, broadly speaking, about structure formation, about the formation of galaxies and the role that massive black holes play in the formation of galaxies. And this is work I've been doing over the past, I don't know, 5 years or so. And obviously it's a huge topic. So I want to acknowledge that it's not just me doing this, but a lot of collaborators, and these are just the collaborators that contributed to the stuff that I am presenting today. And I want to particularly highlight the 3 people here, Christian Ehlert, Deepa Pathak, and Magda Schivek, who are students I've been fortunate enough to work with. Christian and Magda, graduate students, and Deepa is an undergrad student I've been working with in the past year. So generally speaking, what are we trying to do? So the idea is that we take the cosmology or the cosmological perturbation theory and evolve structure forward in time to simulate like the formation of and emergence of structures, of halos, and eventually of galaxies throughout cosmic time, throughout most of the lifetime of the universe, like 13.8 billion years. And we want to do so in a computer simulation. So how do we do this? Schematically, basically what we want to do here is to create initial conditions from cosmological perturbation theory. The main reason we want to do this, and this is quite important to keep this in mind always, is like this is probably the most accurate type of, or most realistic type of initial conditions we can get for this particular problem. And this is why these simulations starting from these cosmological initial conditions are so popular. So if we start from there, we want to then use basically our knowledge about the physics of the universe, which on the largest scales is mainly gravity and ideal hydrodynamics, including radiative cooling on an expanding background, and solve these partial differential equations numerically to follow the gravitational collapse of matter into halos and follow further collapse of the gas after losing their pressure support into stars and into massive black holes, follow their growth and evolution over time, and in the end to get out a prediction for a galaxy population which can be compared to observational surveys. So to do this, we want to start out with a cosmological volume which is at least large enough to have like both a statistical sample, but also like large enough to warrant that we can actually capture a representative part of the universe. And well, the absolute minimum, I think, in terms of volume we need for this would be about 100 megaparsec side length, which de facto means that we're simulating in terms of mass in that universe about 1.5 times 10 to the 17 solar masses. So if we then want to simulate, for example, like say star formation of every single star or whatever, like having a mass of a typical mass of a solar mass, you end up with 10 to the 17 resolution elements, meaning 10 to the 7 terabytes of data you have to store just to keep whatever calculation it is going, which is vastly more than we have available at all, about 4 orders of magnitude too much. And this means that realistically, we definitely have to coarse grain at the lower scale end and try to do a simulation just up to a resolution of about like 10 to the 4 solar masses if we just consider the memory limits. In practice, it's more like 10 to the 5 to 10 to the 6 solar masses per resolution element we can afford these days in these kind of simulations. So that's important to keep in mind. And the basic reason for this is really if we start out with the premises of having this large volume and of resolving everything equally well, there is basically no way around making this compromise in resolution. So what we need to do here on the smaller scale, is to find closure models that essentially abbreviate the collapse of a structure into the smaller scales. This as such would not be a problem if we only had like the evolution of large scale structure collapsing down into smaller and smaller scales. You could just add some sort of sync prescription at some point and by this just close off the simulation at the smallest scales. Unfortunately, that is not quite the case, what's happening physically. So there are so-called feedback effects, which are small scale effects that act on galactic or even slightly larger than galactic scales. And these effects need to be taken into account and actually have been proven to be quite crucial for the galaxy formation process itself, which means that this kind of modeling always will require some sort of so-called subgrid models that capture small-scale physics that we don't really resolve and don't really resolve by quite a number of orders of magnitude but that need to be included in these kind of simulations to get anything out that is realistic. So generally speaking, there are two flavors of this feedback, two broad flavors, which by now I think it's reasonably agreed upon what their role is, with stellar feedback mainly acting in making the overall efficiency of baryons converting into stars, cooling down and converting into stars, making that an inefficient process, peaking only here at around like 15 to 20%, and making it even less efficient on smaller scale halos here at the low mass end, while the feedback from accreting supermassive black holes, so-called AGN feedback, mainly acts on the high mass end on massive galaxies, galaxy clusters, and mostly also at lower redshifts. Though there are some debates where there are other areas where this is important as well. But for a global population statistics, that's the main thing to think about. So as I said, this picture is reasonably agreed upon by now. As a matter of fact, there are a number of simulations that follow this kind of broad approach to modeling galaxy formation. Here are just a couple of them. They all agree upon this combination of stellar and AGN feedback. They all disagree upon the exact implementation of how this is modeled. And they're also slightly different in some of the numerical aspects, some of the focuses, what their main research interest is, and well, also their favorite color scheme in their projections. But other than that, I want to emphasize that a lot of what I will be talking about in the following could be done with any of these simulations. I will be mainly talking about one, mainly because I'm part of it. And the simulation I will be talking about is the so-called Lustrous TG Project, which is a project that started out in around 2015 with a group here of 11 people. And we have been running 3 main simulation volumes, varying size and varying resolution to capture everything from like relatively small, though not quite the smallest dwarf galaxies, to galaxy clusters in the largest volumes. And the first results were out around 2018. By now, all the simulation volumes are publicly available. It's quite a lot of data, like each and every single volume here has like a couple of 100 terabytes of data. So that's a pretty massive amount of data, but there are quite convenient publicly facing interfaces also to get like individual galaxy data, post-process data and stuff like this also publicly available. So this was quite a success also in terms of usage in the community. So by now we have more than 300 papers making use of either the model or the data itself. I'm only part in a tiny fraction of them myself. I don't know all of them. And in this talk particularly, I will only cover a really tiny aspect of the simulation itself. There's a lot more that can be done with these kind of simulations. So if you're interested, generally, I'm at CITA now, so come and talk to me. Always happy to help or to find new creative ways to use the data. So what I want to talk about mainly is, well, as I said, my interest is this kind of subgrid modeling, and in particular the modeling of massive black holes and AGN feedback. And as also mentioned, this is mainly acting on massive galaxies and galaxy clusters. And one way this manifests itself can be seen here in galaxy colors, here in the colors as a function of stellar mass in a paper by Dylan Nelson, where he compares the galaxy colors with observed SDSS galaxies, finding a reasonably, or actually quite good agreement with this blue sequence of star-forming galaxy and this red sequence of quiescent massive galaxies. And we can show, or I showed this in the model paper itself, but this is clearly, this bimodality and the emergence of this bimodality is clearly linked to the introduction of an efficient AGN feedback channel. Speaking of this AGN feedback, let me spend a few words on the modeling itself. I don't want to go into all details, but some things are quite helpful to realize what we're actually doing here. So broadly speaking, we estimate the gas density on kiloparsec scales, which is roughly the resolution scale, a bit larger than that. And from these gas properties in the galactic center, we estimate an accretion rate, and this is simply done using a very simple Bondi formula. From this accretion rate, this accretion rate, I should say, is Eddington limited, which is important for higher redshift. So we have a black hole growth rate here. We use a fixed efficiency then for feedback onto the galaxies themselves. And one of the key features and that I've been working a lot about on is like there are two modes of this feedback. And what we postulate here is like we call it like a mode inspired by luminous AGN, some sort of quasar mode feedback, which is just modeled as a thermal feedback. And then we have a second mode, which is a kinetic wind mode. This is really inspired by low luminosity AGN driving like rather uncollimated outflows magnetocentrifugally, but potentially could also represent things like small scale jets that get dispersed on sub-kiloparsec scales also. What this model itself is doing is essentially kicking surrounding gas cells, well, driving them to velocities of several thousand kilometers a second to post-shock temperatures that are super variable. And the main heating mechanisms, primary heating mechanism, I should say, is through shocks. Though then as a secondary effect, you get like outflows through this overpressured hot gas as well. So that's basically what we're putting in. And we can now look at the galaxy population and try and understand as the first step what we get out from this model itself. So looking here at the specific star formation rate as a function of stellar mass at different redshifts, redshift 4, 2, 1, and 0, what we see here is a so-called star-forming main sequence here, which kind of is present at all redshifts, though redshift evolving to lower normalizations at lower redshift, which is expected. And then we have an emergence of a population of massive quiescent galaxies here. I should say I exclude satellite galaxies here. So they are just these massive quiescent galaxies that are like quiescent. And they are emerging, like the first ones around redshift 3, redshift 2-ish, and more towards the lower redshift. And if we follow them back in time, which we can do in the simulation, and in particular, if we then also track the individual energetics of the different feedback channels in these galaxies, we can actually clearly associate, though I don't show this in these two plots that clearly, that the emergence of this quiescent population is linked to the kinetic AGN feedback, the blue line here. So I've explicitly shown this in this paper as well. So this particular mode of feedback is responsible for the quiescent population in the simulation. I'm not claiming anything here about that this has anything to do with reality yet. And this brings me already now to the next steps here. So what we want to do now is to test this model with like as challenging of observational probes as we can, essentially. And I want to present to you a couple of studies now related to this. And well, some of them some of the ones I'm most excited about. There are more than that. So the basic idea here is really to, well, the most strict or restrictive tests might be during the process of quenching itself, whether we get that right, and the properties of galaxies during quenching. So that's essentially what I'm trying to get at. And the first study in this direction that I want to present here is that by Erica Nelson's recently published. So we have again here here it's just star formation rate, not the specific star formation rate, but it's kind of the same thing. And here the stellar mass. We have medians here, like theory prediction, and actually the black one is the most recent, the most recent analysis of the observational data. There have been some issues in the modeling that have led to some shifts in the observational predictions as well. It's kind of scary how close they line up. It wasn't quite intended like this, but we knew already that they're pretty close to this. And this is to a certain degree, as I said, by construction. But what we can do now here also, and this is done, she did this both in observations and in the simulations, is to divide up the sample of galaxies by their distance to the star-forming main sequence into galaxies that lie above the star-forming main sequence, on the star-forming main sequence, and below the star-forming main sequence. And then stack them and try to infer radial profiles of specific star formation rate. And this is what is shown here on the right. For galaxies above the star-forming main sequence, having here this slightly rising specific star formation rate, and at the main sequence roughly flat. Below the main sequence particularly, you have this dip in specific star formation rate, which is kind of or what we suspected to be caused by a centrally concentrated AGN feedback. And one indication that gives us confidence that this is actually really related to the AGN feedback itself is that our previous generation of simulations which most notably has a different AGN feedback modeling, which is acting slightly off-center, actually not so much centrally concentrated, does not have this dip in the central specific star formation rate. However, like the simulations and observations seem to agree reasonably well, though I'm not sure this discrepancy here is something that needs to be looked into, but this might be actually something that is real as well. So that was like a first test of something that we really didn't like think about when we built the simulation beforehand, but really just recently came up with as a test, which is here constraining the star-forming gas, and this is actually redshift 1 galaxies here. So as a second test, we can look now not at star-forming galaxies, but actually as quiescent galaxies, and we do this here at redshift 2 actually, where observationally there is quite recent studies by Ransus, here a paper on 2020, where she looked at well, quiescent galaxies, in particular also recently quenched galaxies at a high redshift, and measured their, or compared their half mass and half light radii, finding that there is actually a trend of this ratio with the age of the stellar population of in these galaxies, meaning essentially it scales with how long ago the galaxy was quenched. And this gradient here between half mass and half light at a specific band means that there is a color gradient throughout the galaxy. And the color gradient can mean basically three things: either some dust attenuation, which is radially dependent, which would be unfortunate, some metallicity gradients, which interestingly are also then different between the different galaxies here, or age gradients in the stellar populations. So an undergraduate student that I worked with last year, Deepa Pathak, looked into this, and well, she first made this plot, like just trying to reproduce what has been observed observationally, and it turns out that in the simulation, at least qualitatively, the same trend is reproduced with a significantly smaller scatter here, I should say, but the smaller scatter might be just due to the substantial observational uncertainties. Who knows? But what we can do more than just comparing this particular data here is to then go and dig deeper into the simulation why this is the case. And particularly, it's as easy in the simulation to just plot the age gradient itself. And I want you to look at these three panels here, which is the quiescent galaxies and the median stellar age of these quiescent galaxies. Just look at the solid lines. The others are not so important for now. Here again, there are three different bins in galaxies, quiescent galaxies of different age. So the young quiescent galaxies have flat to slightly rising ages, while the intermediate and particularly the old quiescent galaxies have declining ages with radius. So this was one of the possible causes I discussed in the last slide, and it seems that it's actually happening in the simulations as well. And we can do actually more than that, or the Deepa found more than that, that among the young quiescent galaxies, not all have like this rising stellar ages, but actually there are two populations, and only one of the populations, contributing roughly half of the sample here, has these rising gradients, though here also there's a lot of scatter from galaxy to galaxy. And the determinant factor for this are actually recent, quite significant mergers of galaxies. And she could then show also in a lot of detail here, I don't want to go into all the details, is that this recent merger is coincident with a starburst in the center which then causes the stellar ages in the center to decrease. And subsequently, these galaxies quench, don't form any more stars, and that's how you end up with like these rising, with younger stars in the center and older stars in the outskirts. And she then also shows, like, goes on and showing like the natural secular evolution of galaxies is that the age gradients become steeper and steeper, and this is likely due to just cosmological accretion of younger or lower mass galaxies. So I really like this study in particular because of the methodology we could apply here. It's like we started out with an observational effect, just checked whether the simulation gives you similar effects, could really discern what exactly is going on in the simulation. And we are currently really working on making specific independent predictions for independent observations, like the merger non-merger thing. And one obvious thing would be like just looking for signatures of this. And we're currently working on how exactly to do this best at high redshifts, which is probably challenging and will probably involve some future generation of telescopes. But that might be a very specific thing to be tested. And obviously the connection of merger and quenching, but quenching again just means is specific to the exact modeling of AGN feedback in the simulation, is something that is a very strict test to the AGN feedback modeling. So speaking of more observational data, a third test we can try to do, and also this is at a high redshift or at cosmic noon. And this is an upcoming, hopefully upcoming observational program. It's a Cycle 1 program with the James Webb Space Telescope led by Sirio Belli. And what he proposed to do is to get spectra for around a bit more than 100 massive cosmic noon galaxies, get very deep spectra for them. And with these very deep spectra, he's able to infer star formation histories for these galaxies. And the idea here is really to look at things like the time scale at which these galaxies stop forming stars, meaning quench. And so the idea here in the last two examples was really to probe AGN feedback via the spatial distribution of stars and gas, and now we are looking at the time series behavior essentially of galaxies and whether that's kind of in agreement with observations or not. And my contribution to this particular projects are the green lines here, which are zoom-in simulations I have run, not just 3 of them, but actually 15 of them, spanning a quite large range of masses from 10 to the 9 to 10 to the 12 solar masses in stellar mass. And these zoom simulations were run like the last half year or so while I was still at CFA, and I'm currently in the process of looking at the data. The special part of this simulation project is that I don't have only these 15 halos, which is kind of interesting, but then also have different models of AGN feedback on top of them, and a direct comparison between the different feedback models. And different feedback models does not mean like just a slight variation of some parameters or whatever, because I mean, people have done that. First of all, the problem with this approach is usually what you do is you end up altering the redshift 0 galaxy population completely and bring them in complete disagreement with observations. So that's not really helpful at all. But what I wanted to do instead is to build a new AGN feedback model which works significantly different, however, is constrained still by a certain set of calibration parameters, which are usually at redshift 0. And so they're kind of recalibrated to produce more or less the same redshift 0 results. And this way, I hope to be able to really assess the uncertainties in AGN feedback modeling at high redshifts, and well, how much degree of freedom do we have there by so far not having many constraints directly at these higher redshifts. As I said, I only just started looking at this, so I don't have a lot of results there, but let me briefly discuss here which kind of models of AGN feedback I'm talking about here, what kind of level of variations I'm talking about here. So the first model is what I already talked about as used in Lustrous TG. The main point for starting with this is that we are then able to, well, each zoom simulation is just one halo, and you never know like how special a halo is in a certain way. So by having the same model as the cosmological volumes, you're able to actually specifically check how special a specific zoom simulation is. So you always have like this comparison option there, which is quite useful. Then I have a second variation, which I call QW here, is kind of a quasar wind. And the idea there is really to have a model that is efficient at high accretion rates, at high Eddington ratios particularly, which kind of is a more mainstream idea currently for AGN feedback in general in the AGN community, of like luminous AGN driving fast winds into the galaxy, and this causing the feedback effects. And I ended up with using this as a single mode model, actually, with just this quasar wind. And most importantly, there is no switch between modes, and the energy that is injected at a given for a given black hole is really just proportional to the accretion rate, which is not the case for the Lustrous TG model. So I expect, or the idea is to expect the feedback effects to happen at different times, at different physical conditions, actually. The third model, and I've only run a couple of simulations of that one, is not so much changing the conditions where feedback is active, but actually changing the way feedback acts. So I'm switching here from a kinetic wind, which really acts very centrally, to an explicit jet modeling, which is actually inspired more by galaxy cluster feedback, and I'm just essentially testing where a feedback model that kind of is more originates from the idea of collimated jets is actually able to replace our wind model and actually quench galaxies. So that was the main question for the third model. And there is always then the possibility here, given that these are zoom simulations and each individual simulation is kind of only moderately expensive computationally, to add more models to the mix, depending on how it goes. But that's what I'm currently doing and probably will be doing in the next year or so. So let me give a brief summary so far, what I've talked about. So the global properties of galaxies, and I've just shown you two plots, like the stellar mass fraction as a function of halo mass and the galaxy colors. They're pretty well reproduced by now by cosmological simulations. There are a bunch of more like observables you could compare to, but we're actually pretty happy with the agreement. A lot of this agreement is certainly by construction, since we really explicitly looked at it when building the model. So what we are trying to do now going forward is really to find more challenging tests and trying to essentially disprove our model. And one approach that I'm excited about is like really looking at the galaxies where AGN feedback is most relevant, looking at the spatial distribution of this. I've shown you redshift 1 galaxies and the star forming phase of those redshift 1 galaxies, quiescent redshift 2 galaxies and their age gradients, as well as upcoming observations with JWST, probing quenching timescales and things like this. And I am very interested also, like from a simulation perspective, in now not just use or being happy with one specific model, but actually quantifying the uncertainty in our modeling and how well do we actually know that this specific model is a good model, or could we just reproduce this with any model whatsoever? So I'm really interested in doing model variations, but I think they need to be really always constrained by redshift zero observations, where we have like quite significant constraints already, but there's always a possibility that reproducing things at redshift zero doesn't mean that the way you get there is correct. So with that, I would like to just ask whether anyone has any questions to this part before going on. And I don't see anyone. So
there's a show of hand. Please unmute yourself.
Yes.
Yes.
Hi, Rain. I'm Salvatore. I just want to ask you a question. So you with your model prove that in TNG the only way to quench galaxies is via the AGN feedback. I was wondering why is the thermal mode not doing any damage to the star formation of galaxies? And if a model that would imply, like, for example, some wind, even in the quasar mode, could be more natural for explaining the diversity that we see in observations. So the question basically is, so in TNG, you have a strong threshold for switching between the two modes, but this is converted into a very specific stellar black hole mass where you have the switch between the two. That is not natural and not observed in real observations. I was wondering, what about a mode that is intermediate between the two in intermediate black hole mass?
Yeah. No, this is a really good question, because this is actually exactly what one of the reasons why I started this variation here. So yeah, as you said, there is this weird mass dependence of a switch of modes, which translates pretty directly into a stellar mass dependence of all kinds of galaxy properties, and it is there by construction, and we do not have a particularly good motivation for it. So the question is, do you need this at all? And related to this is like also like the quasar mode feedback we're using here it's actually a very old implementation, and an implementation we know that is not doing much for most of the galaxies and only doing some work for like the most luminous AGN. So first of all, if we just use this particular quasar mode implementation and nothing else, we will not reproduce the redshift zero galaxy population. What I try to show here, although the plot is not particularly large, so with this second model here, what I'm trying to do here is changing exactly these 2 points, using a quote-unquote quasar mode, which is just winds as well, and getting rid of this threshold altogether by just using winds throughout, no matter what accretion rates or anything. And you don't see this very well here, but like I'm comparing this, I need to recalibrate a couple of things, but actually not that significantly. So the overall efficiency of the feedback needs to be a bit lower, for example. And here it's actually the red line, which is this only quasar wind model, which gets a bit of a delayed black hole growth. But in terms of stellar masses like coming out, it is possible to reproduce what the Lustrous TG is producing quite easily, actually. I was rather surprised that this is not that much of a problem. There are a couple of interesting effects, and these are just small volumes, so it's hard to really know how robust all of this is. It seems like the gas mass in like ellipticals might be a bit different, like in terms of gas mass in our 500 and stuff like this. But generally speaking, yeah, this is exactly the reason why I try to do this model variation.
Okay, thank you very much.
Are there other questions? Again, I don't see anyone, so the moderator has to do that.
Yes, Rainer, please go ahead. We
Okay,
have
so
about 15.
yeah, with the rest of the time, yeah, I want to mention something that I haven't been talking about at all, but it was in the title. What about the physics? We haven't really talked at all about whether what we put in there in terms of modeling is viable at all in the first place. And this is obviously something that is a bit worrying, since, well, if you kind of can build a model that is unphysical but reproduces the global galaxy population, it's not really worth a lot. And it's a pretty tricky business to actually check whether the model itself is viable. And I think what you need to have to do is to go to individual cases and try to do more simplified or connect to more simplified simulations where you actually capture the fundamental physics of feedback itself. And I'm showing now this with a specific problem, and these are, well, I chose this because it seemed the easiest at the time. I still think it's the easiest. And this is a case of massive galaxy clusters, and in particular of massive cool core galaxy clusters, where you have the so-called cooling flow problem, well, which has been around for some time. It's just the idea that the X-ray luminosity from the cooling gas, the hydrostatic gas here, suggests that you would have like thousands of solar masses per year of star formation, which you don't. And well, but you have these strange X-ray dim bubbles, which are jet inflated globes, and these energetically match up quite well with the cooling luminosity, basically indicating that these AGN jets and the subsequent bubbles are responsible or deliver the heat for reducing the overall cooling flow in the galaxy cluster, and thus reducing the star formation in them. The main motivation of doing this, or of looking at this first, is the accessibility observationally of the hot volume filling component in the X-rays, which helps a lot. So we don't have to. It's kind of easier if you just need to look at the gas in hydrodynamic simulations and don't have the translation to stars and all of this. Another motivation for this is that while I think we are doing a remarkably good job in reproducing galaxies, we have some indication that for the most massive galaxy clusters, there might be some potential discrepancies we're getting. In particular, we're not really getting high enough densities, central gas densities in the most massive cool core clusters. That's, you can argue a lot, like all the kind of analysis and whatever going on, how much of a problem this is, but this is kind of a feeling that there is some tension here as well, which also motivates digging a bit more into the physics of this. So what I've done here, and I started this also quite a while ago already, is to take a step back and try really to, well, we know essentially in these galaxy clusters that the jets supply the energy, they inflate these cavities, and this somehow gets then distributed throughout the cluster and reduces the cooling flow. We don't really know how this is happening. So the idea here is just pretty simple. Just, okay, we know how to simulate jets. We know how to simulate galaxy clusters. So let's just combine these two things, which sounds simple. It's not quite as simple as it sounds, mainly due to the vastly different scales of these two things. And in particular, if you really want to do a good job in simulating jets, you need a lot of resolution. And by the way, simulating jets here just means simulating the outermost phase and the deceleration and stopping of the jet, not really any launching or anything, early propagation of it. But you can do this, and by now I am able to do this in a series of simulations of different complexity and different resolution. With on the leftmost panel is just a simulation of a jet that as higher resolution as I can afford, essentially, but really just simulating the propagation of this jet, and it's purely hydrodynamic in this case. And the main point here is to just resolve it as good as possible to see or to get a numerically converged result in terms of jet propagation, which I'm able to get since quite recently. And then gradually decrease resolution a bit and increase the runtime of the simulation itself. The simulation is just a stratified medium, and gravitational potential is just an NFW potential. So you can go one step further and like simulate the entire rising of a single jet event and the rising of a cavity and how the dynamics of the cavity actually works. You can do this including radiative cooling in the halo, and this is shown here in the center. Like compare the effects of the jet on the cooling time. You can really do really careful study of the resolution need in like jet resolution, in halo resolution, and stuff like this. And also in modeling parameters, you unfortunately even there don't really get rid of modeling parameters. And most recently, and this is work led by Christian Ehlert in Potsdam at AIP, also run this in a isolated galaxy cluster for a couple of giga years, where we are getting here there a couple of X-ray projections of well, these bubbles happily bubbling up and actually reducing the star formation rate to like 10 to several tens of solar masses per year. So actually to the degrees where we actually want to get at. And what I'm currently doing, and also it's probably something that will be going on for the next year or two still, is to try and run with the same model then a cosmological zoom simulation of galaxy clusters using that model and trying to see whether that produces cosmologically also anything realistic or not, and then also compare to the our current cosmological simulations and how the models differ.
Question?
Yeah.
So how does your model decide? I mean, I understand you can do a focused model of jet interaction in a group or cluster where you put in the jet, but do you have a deterministic way of deciding whether or not a jet is emitted in a larger scale simulation?
Yeah, it's always active. It's like you have for this self-regulated simulation, you have basically an accretion rate estimate, and then you have well, the estimate of the accretion rate times some efficiency, which is still a parameter. It gives you a jet luminosity you have, or jet power you have, and this jet power is then just injected. And the only way you do not have a jet active if the accretion rate is actually exact zero, or if the jet model detects like, oh, I'm not even able to launch anything because the coarse graining, like the resolution requirements that I need, means that I have a certain quantized energy requirements, so I can't even launch anything.
Sure, but do you think that's going to be realistic enough?
Yeah, I mean, judging from recent radio observations, like the fraction at which jets are active at the highest mass scale is reasonably consistent with unity. And well, observationally being active is always a function of sensitivity. So I think it's not a bad approximation. Maybe it's just active 50% of the time. That might be possible, but I don't think that would change things like massively. If it was just active like 1% of the time, yes, that would change things, but that won't work.
Thanks.
And, yeah, so I actually want to finish up basically. So what I've presented here is like a first attempt of combining like idealized simulations with cosmological simulations. And I'm not quite at the cosmological simulation stage yet, though literally today I got the initial conditions for them. So the idea there is really to identify a specific system we want to model, try to simplify it down to the level where we understand the physics, and then have a whole set of simulations of different complexity to really understand all processes in between, to actually hopefully in the end make a statement about how realistic or unrealistic our large-scale models are actually at a given, though this is always a statement of a given environment at a given setting. That's unfortunately always the case. And I plan to do a similar thing while I'm at CITA, also with black hole accretion. I don't really have time to talk about this here, but that's something I'm very interested in. And so it just come to the summary, and just a couple of points I think I want you to take away from this talk. First, I already mentioned it, I think it is possible now to simulate a realistic galaxy population from cosmological initial conditions, and we can debate what realistic is. But I would say that was definitely not the case 10 years ago, which leads then to the first point in the next steps, that connecting cosmological simulations to observations is now a way more promising endeavor than it was back then. But this also requires, and this necessarily requires and will require for some time, sub-resolution models. And these are unfortunately poorly understood. And therefore, I think it's really important to try to connect the large-scale simulations with small-scale, more controlled, more idealized simulations. Thank you for your attention.
Thank you so much, Rainer. Let's all give Rainer a round of applause for giving such an interesting talk. And any questions, because we are a bit running out of time. But yes, any question? And for anyone who wants to have a longer discussion, please feel free to stay longer.
Well, I'm sorry, because of other constraints, I missed the first 15 minutes of your talk, but maybe you just address this. But to what extent are these models constrainable by, more detailed observations of nearby AGN hosting galaxies, where you can study the structure in more detail?
Yeah, so you missed this because I skipped it to a certain degree. So I think one of the key challenges, and this is one of the reasons why I want to go a bit more into the black hole accretion, and this is a recent plot here on the right by Melanie Habouzi. And what she's showing here is like the mass function of luminous AGN at redshift 0. And unfortunately, different simulations give vastly different different predictions here. And what's going on here is essentially we understand the small scale accretion physics so badly, and we model it rather simplistically, but while we might be getting something like a global black hole accretion rate density also right, the actual instantaneous luminosities, I don't trust them at all. Which also means like the connection of galaxies and luminous AGN is probably not particularly well modeled in this sense. So I think we need to do a lot better in terms of understanding gas inflows into galactic centers to get better in this respect. And I'm not sure whether this is like constraining in this sense. It's just like it's a lot of numerics in there that well, there are some model choices here, like this cutoff here is something as a model choice, but a lot of the other things I think are also like numerics and small choices there.
Any other question from the floor? Ryan, I do have one question. Like you mentioned, there are a number of different simulations, and like, how do we pick? Let's say if someone is interested in galaxy cluster, like you do, so should they have a look of all different types of simulation and decide which one to use, or like, given you're an expert in the field, what are your guidelines?
Yeah, one deciding thing is the public availability and how easy it is to get them. Another one is the availability of a specific volume and a specific resolution. So while a lot of them have like this about 100 megaparsec volume, that's really not quite enough to get, if you want to be interested in galaxy clusters, so you need a larger volume than that. If you say you need at least like about 300 megaparsec side length resolution, you are constrained currently to Lustrous TG or Magnetic Convert. I think the other ones don't have comparable volumes. So it kind of is a bit restricting, like what exactly you're looking for. The galaxies themselves, there are a lot of different ones, and you can use whatever you like. The other thing is like being familiar with the implementation of and the assumptions in the feedback models helps a lot. So you need, like, choosing one that you actually know best might be a good idea. Yeah, that would be my recommendation.
Yes, thank you so much, Ran. I should stop recording, but please feel free to stay and ask further questions.